Each year, the world's top bicycle racing event, generally considered to be the Tour de France, is held in France during the month of July. In this video, we'll look at the gear systems of bicycles. This video is part 3 on bicycles. Here is the familiar looking gear system of a bicycle. The driver at the front is moved by the pedal powered by the bicyclist, and so is the driver. The driven is at the back. Notice that the presence of the chain makes the rotations A and B go in the same direction. This is different from the gear train we learned about in the introductory video. The spur gears move in opposite directions because they are meshed together. In bicycles, the word sprocket is the general term for the front and back toothed wheels. However, in the cycling world, although sprocket is a perfectly good and well understood term, the sprocket at the front is more commonly called a chainring. I suppose it looks like a ring with a chain around it. The rear sprocket is more commonly called a cog. The good thing is that the gear ratio calculations are the same on bicycles as with gear trains. Sprockets, cogs, chainrings come in various designs. They must be shaped just right to fit the chain that turns them. During this video, I will sometimes use the term sprocket as a synonym for cog or chainring, just to keep these terms familiar in our minds. Now here's a picture of an early bicycle, 1885. It was a bit tricky getting on one and maintaining balance. It was called a penny-farthing bicycle or a high wheeler. It was also officially called the ordinary bicycle. It had no gears. The pedals were connected directly to the front wheel, making this a direct drive bicycle. Now I can't resist showing the next clip of a penny-farthing race in 1928. And these races, they continue today.
The penny-farthing was the first machine to be called a bicycle. They're old, they're funny, and for some, still a big deal.
People find the penny-farthing almost hypnotic. I don't know why, I can't explain it, but people just love seeing it. I'm the current UK champion, so I've got a title to defend.
But penny-farthing racing isn't as easy as it looks, and it sure doesn't look easy.
It's a very dangerous machine to ride. You're sat up on top on the point of balance virtually, so if anything goes wrong, you tend to be going headfirst over the front of the bike.
And here's one final clip showing the learning process for getting off and on this bike.
Oh!
Bit more. Bit tentative.
Oh! There's my...
Get on the seat before you run out of puff.
That's right, yeah, it's easier than it looks.
Okay, full beans, full chap.
Do we do a risk assessment, John?
2, 1, push, push, push. Come on, let's get it going. That's it, join the pedals.
Oh, yes! Oh, my God! Oh, wow! Now I've got to stop, right?
No, don't stop.
Well, I want to be part of the club.
Yes, so you have to dismount, you don't stop.
Oh, I see what you mean.
At walking pace, reach back for that peg with your right foot.
So, hang on a minute, we'll do one more lap.
Okay, now straight line, bit faster.
Okay.
Right foot, reach it back. Left foot, and off. There you go. You're in the club.
Yes, I'm in the club! Thank you very much, cheers.
The reason for calling these bikes penny-farthings is shown in this picture of a large penny in front of a small farthing behind it. You can see the resemblance. In the late 1800s, the penny-farthing bike was replaced by the so-called safety bike, in which a chain and sprockets were introduced so that the wheels could be smaller and of equal size, thus making it more stable. Today's bicycles look very much the same. This one has only one gear, as there is just one sprocket front and back. Let's now look at the simplest situation shown here. One sprocket on the front, which is the driver, and one in back, the driven. The gear ratio, based on number of teeth, is 20/12, which simplifies to 5/3. The ratio is 1.66 to 1. In terms of rotation, This is where the interpretation differs from meshed gears. The introduction video on gears showed that when looking at a ratio in terms of rotation, the first number referred to the driver. But with chain gears, where both sprockets rotate in the same direction, the first number refers to the driven or rear sprocket. So here, the driven or rear sprocket turns 1.66 times, while the driver or front sprocket turns once. A bike like this, or the previous blue one, has only one gear, so gearing up or down is not possible. When more sprockets or cogs are added, the gear ratios can change to allow the cyclist an easier time riding uphill, downhill, or level. In this picture there is one sprocket at the front and 9 sprockets at the back. So there are 9 different gear ratios available. This makes it a 9-speed bike. A set of sprockets like this is also a cassette, or less commonly, a cluster. Here we have 2 chain rings. The total number of gear combinations is the product of chain rings and rear cogs. So for example, 2 chain rings times 9 cogs on the cassette gives 18 possible gear ratios, and hence an 18-speed bike. The chain is moved by the cyclist using what is called a derailleur, which is operated from the right handlebar. Each click of the derailleur will move the chain 1 sprocket lower or higher. Now let's delve into the gear ratios. Here is the front with 2 chain rings, a large one with 50 teeth and a smaller one with 34 teeth. Here is a 7-cog cassette. Again, cog and sprockets can be used interchangeably, with the smaller cog having 11 teeth and the largest with 21 teeth. The highest gear ratio is obtained when the chain links the largest chain ring on the front with the smallest cog on the cassette like this. The ratio is 50/11 or 4.5 to 1. This will be the highest gear on this bike. When the driver is large, we recall from the introductory video, the force produced is small, so this will require the most pedal force to turn the chainring and is therefore best for speed. The ratio tells us that each time the chainring turns once, the small cog will turn 4.5 times. Let me illustrate this here. The chain connects the 11-tooth cog with the 50-tooth cog to give our 4.5 to 1 ratio. The blue circles are the cogs in a 4.5 to 1 ratio, and they are to scale. When the animation starts, you will see the large ring make 1 turn, while the small one makes 4.5 turns. The distance traveled by the wheels is the straight green line. Now don't confuse the rotations of the cogs and chainring with those of the wheels. Both wheels will cover the same distance in the same time, and I will come back to this later. Now let's connect the smaller chain ring with the largest cog at the rear. This gear ratio is 34/21 or 1.6 to 1. This gives the lowest of the gear ratios on this bike. Less pedal force will be needed to turn the front wheel, so this combination makes it easier to go uphill. Let's now look at this simulation. Now the chain connects the smaller sprocket on the front with the largest cog on the back. The gear ratio is 34/21 or 1.6 to 1. Again, the larger blue circle is the 34-tooth chain ring, and the smaller one is the 21-tooth cog. The smaller circle made 1.6 turns to the larger one's 1 turn. Notice how the distance traveled was less. This shows less distance traveled than the higher ratio which means for the same time interval the speed was less. I've talked about how the chain rings and rear cogs can rotate at different speeds according to their gear ratios. But how do the wheels themselves rotate? They certainly don't rotate at different speeds, as we know from experience. Both wheels move together. The front wheel takes its lead from the rear wheel. Here's a comparison of the wheel movement in each case. The bicycle's front and rear wheels will be represented by the one wheel shown here. The 4.5-to-1 ratio means that the bicycle will move a greater distance for one revolution of the pedals than the bicycle with a 1.6 ratio. Watch the air valve at the bottom of the tire as the tire moves. It will turn one revolution in 3 seconds. What you see will be what is happening to both wheels at the same time. Now suppose we switch gears on this bike to a 1.6-to-1 ratio. What you will see will again be what both wheels are doing. The movement will be for the same 3 seconds. You noticed how the wheel in the top case moved faster than the bottom one. That's because the diagrams are close to scale, so the movements are quite accurate. The distances show that the top bicycle covered more ground than the second one in the same time because of the higher gear ratio. Other chain drives. The bicycle isn't the only case of a chain drive. We see them in garage door openers. Belt drives are much quieter than chain drives and are becoming more popular as a result. Here is a chainsaw. And here is a timing belt in a car. In this case, it is not a chain, but a belt that connects sprockets, just like the garage door opener. To end, let me make a brief review of some of the terms. First, as a single item, this is a sprocket. When put in a bicycle, at the back, the sprockets are referred to as cogs. The front sprocket is referred to as a chainring, or chain rings if there's more than one. Several cogs like this are called a cassette. Here is the rear derailleur that allows the chain to move from one cog to another. The front generally has between 1 and 3 chain rings. These terms are common in North America and specifically Canada, where this video is made. Other parts of the world may have slight variations on these terms or how they are used. And this concludes the video on gears on bicycles.